Welcome everybody to the afternoon session. We have one talk now, and then we'll have a coffee break and some more talks after that. So the first speaker this afternoon is Dionyssis Mantzavinos from the University of Kansas, and he's going to speak about long-time asymptotics for the integral focusing NLS equation and other equations. Dionyssis,
Peter, many thanks to the organizer for a series of activities over the past 4 years. Beautiful, great, appreciate all the effort. So yeah, I'd like to talk about the focusing NLS equation and relatives. And the talk has two parts: the long-time asymptotics, and then some more recent work on the proximity of solutions of the integrable model with the non-integrable counterparts. So this is collaboration with all these people. So the first half is more or less with Gino, Sitai, and some of the Stefano. And then more recent work with Derek, Nikos, Jesus, and Yanis. Okay, so let me begin with a very quick introduction, since this audience is, of course, extremely familiar with NLS. So here's the NLS equation in the case of a general power nonlinearity. 3 positive here. Okay, so it's of order 2p plus 1 in nonlinearity. As we all know, it's an important model in mathematical physics with many applications. Plus sign for focusing, minus for defocusing here. And the general case of this power nonlinearity model has been studied by many methods. Especially for this talk, we'll talk a little bit at the end about some analysis methods. But I want to start with the integrable case, which is here for p equal to 1. This is the famous cubic NLS, which is completely integrable, as was shown a while ago by Zakharov and Shabbat. And what this means for the purpose of this talk is that it can be written as a Lax pair, and so it can be solved by the inverse scattering transform. So this is what we need. Before I get into that, let me just give you one of the many results just as motivation. This is a fundamental result by Tsutsumi in 1987 that tells you more or less that this NLS equation on the full line is well posed when the data is in L2, is a square triangle function, for any power between 0 and 2. So this is a globally well posed problem. The solution belongs in this space, but that's not important right now. There's many other works in this direction and more that I won't be able to fit in a slide. But what we're interested in is this scenario, which doesn't quite fit all these works, which is when the initial conditions do not decay to 0 as x goes to infinity. And why are we interested in this problem? So here's one scenario, which is one of the simpler ones. Here you have the symmetric non-zero conditions at infinity. So here we have the same equation. I'm focusing on the cubic case, which is the integrable one. And I'm assuming that u goes to these values, u plus minus, as x goes to infinity, which have the same constant amplitude modulus, which is a positive number, okay, q0. And actually, through a transformation and compatibility conditions, you can first of all see that the initial data satisfies a similar condition, okay, at time t equals 0. And through a transformation, you can convert this problem to a cleaner form down here. So this is still the cubic NLS, but with a modification from the transformation, doesn't affect the integrability. The initial data as before, and now the boundary data, the boundary conditions at infinity are constant and symmetric. So these are constants that have equal modulus and non-zero. Okay, so we want to understand what happens with this problem. Why do we care? As I'm sure you know, this non-zero boundary conditions induce modulation and instability. That's a good reason to be interested in this problem. So if you perturb around the constant background solution at the linear level, at order epsilon, you get a linear problem, which you can solve because the solution goes to 0. So you can use Fourier transform, you solve it. You find this expression, which is not that important, apart from the fact that omega, the dispersion relation here, becomes imaginary for small wave numbers, which means that you get growth as t goes to infinity with this cosines and sines. Okay, so this is the linear stage of modulation and stability, and the question is what happens when the linearization is no longer valid. Of course, cubic NLS is an integrable system, so you would expect it behaves nicely, but you know, this still you want to prove that this is the case. So this is the problem we began studying with Gino several years ago. That this is old work at this point. The modified integrable NLS equation with the initial data. Here the initial data belonging have to satisfy these conditions. So you take away the background or the boundary conditions and multiply with this exponential, and you want this to be L1. This condition has two sources. The first is the inverse scattering, and in addition, the exponential here comes from the way we did the asymptotics. I'm pretty sure it's not optimal, but that was not our focus back then, so you can probably do better. But anyway, this is still a large class of data. And we have the cubic NLS here, so we can do inverse scattering. That was done by several people in the case of non-zero boundary conditions. Barbara is one of the pioneers, and others as well. There was work by Kovacic and Gino on this problem. We had to kind of redo the work because we wanted to do it in an appropriate setting for the asymptotics. But I'm going to skip all the details because I'm going to be sitting alone at dinner tonight, and I will just show you the end product. So in the case of no discrete spectrum, this is an assumption that we make now, but I will remove later. You can show that the solution of the problem is given by this limit, where capital M is a matrix valid function satisfying this Riemann-Hilbert problem. So, okay, so the three components are as follows. It's an analytic function everywhere on the complex K plane, apart from the real line and this segment from minus IQ naught to IQ naught. On these two contours, it has jumps given by the matrix V. I will show them in a moment. And as K goes to infinity, it has this asymptotic behavior. It goes to the identity, plus 1 over K corrections. Okay, so this is the problem that will be working, but one has to analyze asymptotically if one hopes to derive asymptotics. Let's talk about the jumps a bit. This is the one on the real line, and this one in the upper half of the segment, in the lower half of the segment. There's a lot of quantities here, but what's important is the quantity theta, and in particular the exponentials here. So this quantity theta is defined like this. In terms of lambda, C, and K, C is the similarity variable, x over t, and lambda is this square root, and that's the signature of the non-zero boundary conditions. It has branch points at plus minus IQ naught, and in fact, the segment here is really the branch cut for necessary for lambda. So what happens is if you're on the real line, theta is actually real, and you have oscillations that become rapid as you increase t to infinity as we're taking this limit. If you're on the segment, lambda is real again, but k now is imaginary. So theta is complex, and so you get actually exponential growth, which is the characteristic of non-zero boundary conditions. And so this is the challenge for those familiar with long-time asymptotics and Riemann-Hilbert problem asymptotics. This is the novel challenge when you have non-zero boundary conditions. Okay, so very quickly to take you through these results. Our analysis was using the Dionyssis method, and of course there's a lot of work through this method. For us, particularly helpful were these three papers by Buckingham, Benakidis, Lieutenant Nobel, Kotliar, Shevelsky, and Jenkins McLaughlin. We got lots of ideas at different stages of the analysis. The key point is that we have to look at the sign structure of the real part of I theta, because this is what comes into your jumps. So you want to know the sign structure of this quantity. This depends on these stationary points of theta given by this expression. And I'm going to avoid formulas and show you a picture. So as you vary the similarity variable from negative to positive values, this is the sign structure. White is positive and gray is negative. You see that the two stationary points emerge on the real line. As you increase C to this value here, this is minus 4 square root of 2 times Q naught. This is when they both meet on the real line. And then after that, they become complex conjugates all the way up to C equals 0, where they actually coincide with the branch points. And the situation is the same as you go from C equals 0 to plus infinity, just go reverses back. So there's two different regimes, really. There's the real stationary point regime and the complex stationary point regime. And these correspond to different asymptotics. So it turns out if you're in the real stationary point regime, you get the plane wave in the leading order asymptotics. This is the regime described by this inequality. Otherwise, you get the modulated elliptic wave, and that's what's shown in this wedge here. These are the caustics, separating these two regions. Okay, so this is, I'm gonna now throw a big theorem just to show you the full result. But what's the takeaway from here is that if you're in the plane wave region, here I have it on the left half, the x negative half. I'm sorry, Jim, I know you still don't like how we use x negative in the analysis, and I promise not to do it again. But yeah, so in that case, you have the plane wave I promised. So basically the boundary condition times the phase, which depends on the initial data and on the singularity variable. And otherwise, in the left half of this wedge here, okay, in here you have this messy expression for the modulated elliptic wave, which is in terms of Jacobi theta functions. What's interesting here is that most of these quantities that you see are independent of the initial conditions. The only ones that depend on the initial data are this phase over here and also the offset x. The rest of them are independent, so they only depend on the background. And actually, you can compute alpha r, alpha I, which is somewhere here, yes, and m. You can compute it through these modulation equations over here. Once you feed in Q0, and these are elliptic integrals of the first and second kind, and so on. Okay, so why is this interesting? Because it proves that here's a simplification that you can do for the modulus of the leading order asymptotics in the elliptic wave region, where you can see that you recover the periodic solution of focusing on the less with slow modulation. And these are some plots of these results. So you see that for long times, you maintain a bounded solution, okay, despite this linear instability. Then we decided that we would like to remove the discrete spectrum condition and allow a solidum to interact with the background. So the simplest way to do this is just add a pair of poles in the Riemann-Hilbert problem and the corresponding residue conditions. That's a work with CTI as well later. So the jumps are as before, but you also have residue conditions, and this is getting messy. But let me just show some pictures to describe the results. So it turns out you get 4 different asymptotic regimes depending on where you place your pole. Again, I made Xenon happy by putting the pole in the third quadrant, which I've done on the first. I guess he still wants to talk to me and work with me, so I'm okay with that. So this is the third quadrant of the K plane, and you have 4 different cases. How do you define these regions? The blue curve here is the real part of I theta equal to 0 when you plug in the critical value of C that I showed you earlier, the minus 4 root 2 Q naught for C, and you evaluate, and you draw the contour, real part of I theta equals 0 there. You get this blue contour over here. And the green contour is the path that the point alpha defined as alpha r plus pi alpha I, complex point, with the alphas given here. This point alpha follows as you increase C from that value to 0, it follows this path. It coincides with the lower branch point. And so this is the path of this point. And so yeah, it turns out that depending on where you place your pole, you get different asymptotics. And here are some more pictures to see how this happens. So the poles are now in blue. And what's important is, so these are relevant to leading order only when they are crossed by a 0 contour, a contour where the real part of I theta is 0. Otherwise, they are not relevant. I learned from Peter's paper that there's a trick you can do. Even if you have growth, you can convert into decay because localized. So there's a transformation you can allow you to handle this. So the only time you have to to put this in the leading order asymptotics is when they are crossed by one of these contours. So you see, so here at this point, the soliton is not seen in the asymptotics. It's seen for the first time here and only time. And this crossing here happens in the plane wave region while the stationary points are real. And then it keeps going and the plane wave region emerges and everything is, but these poles are on the side, they're not relevant again. We call this is when you're in the first of these regions, D1. We call this the transmission regime. You'll see why in a moment. The D2, it's a plus here. Yeah, this region here is the trap regime. So what happens here? The only difference between that and the previous is that the crossing of the poles happens after your stationary points are complex. So it happens over here. So the soliton arises inside the modulated elliptic wave region. That's the only difference. And here are some numerics to see what happens. So here's a transmission regime where the soliton goes through the modulated elliptic wave wedge, and this is actually a density plot of the modulus. So you can see it going through an alter. This is a plot that shows the phase shift that the soliton induces to the wave in here, and that's a plot that I don't know if you can see very well, shows a position shift induced by the soliton. That's in the transmission regime. In the trap regime, the second one I showed you, the soliton arises, enters the wedge and stays there forever. And here you see the interesting phenomenon. Well, you still have phase and position shift, but also, I don't know if you can see the dashed line is the original soliton velocity, but actually the soliton is slowed down. It's slowed down as it enters the wedge. So there's a change in the velocity. And there's two more regimes that are interesting, and the mixed regime. So what happens here, as I'm running out of time, is that the crossing happens. Okay, so these are regimes where the poles are close to the branch. And in this first case, the poles will be crossed by this zero contour like this here. But then they are crossed again at the second time by this green contour, which I have not introduced what this is. It has to do with the G function mechanism of the problem for those familiar with the asymptotics, but in any case, this is also a zero contour. So at this point here, you get a second leading order contribution to the problem. And this can happen, okay, so this is one way this can happen, this double contribution. There's another way. So because here you see that the crossing happens in after the stationary points are complex. But in this case, the crossing happens over here while the stationary points are still real. And then you have your second contribution as well. So this is a transmission regime with some other stuff happening, which we call wave. And here are pictures that show this better. I'll start with the transmission wave, where things are cleaner. So here you have the soliton again as before, but now it creates a disturbance inside the elliptic wave region as well. And you can see this even here with the phase shifts and the position shifts. So we call these guys waves. In this trap wave regime, it's not that clear. You can kind of see, but it's not as prominent. But you can definitely see the phase and position shifts, the effect inside. Okay, so this is a big summary of the asymptotics. So I don't want to get into more details, but what we proved in these papers was that if you have the integrable model with this kind of non-zero boundary conditions, the solution remains bounded at all times for a large class of data that I explained earlier. And if you have discrete spectrum that we have a soliton, there's some interesting interactions between the soliton and the background, leading to all these regimes. Okay, so then Gino's idea was to look at non-integrable models, because of course these may not be solvable through inverse scattering, but they're important for applications. So we saw earlier the power model, but there's other ones, the saturable nonlinearity NLS, the thermal media NLS, this crazy system that I don't know how it was derived. It's complicated. All these are important in applications, but cannot be treated with inverse scattering. So all this asymptotics machinery is not available. So in this work with Sitai and Gino Sitai and Stefano, we identified some kind of universal behavior across all these models. So I'll show you pictures. So this is the cubic NLS as we were doing before with different kind of perturbations of the background. So Gaussian, such or box-like. You see the familiar wedge forming. Okay, and this is the amplitude versus against X. And then you can do the same numerics for other models, like this is the quadratic NLS with the Gaussian perturbation, or a such perturbation, or the quartic NLS with the Gaussian perturbation. You get the same kind of wedge here. And even better, the saturable model is a beautiful one, the thermal one, and the dispersion managed. So you see some kind of universality here. And that was in 2018, and then I think we kind of left that on the side for other projects. Then I went to a conference in Bremen, SIAM conference. I think I really didn't want to go because it was during the semester and it was inconvenient, but it was great that I went because I met this guy, Nikos Karahalios, who was very interested in exploring rigorously these kind of conjectures. Okay, so his idea was kind of simple or simplistic. Is you take the integrable Cauchy problem over here in the focusing case. You take a general, quite general, non-integrable model, where here, okay, what do I mean by general? I mean that there's the nonlinearity now is not cubic, it's f of mod u squared times u, where f is a function with certain standard properties in the literature. These properties are quite standard when people study this from an analysis point of view. Okay, so you have this general family of non-integrable models that includes the power nonlinearity, the saturable nonlinearity, and so on. And you want to know if you start with data, little u0 and capital U0 that are close to each other, how far are the solutions from one another? And that's I should say this is a different direction than what may be more common in the literature, where you just do a small perturbation of, let's say, an integrable equation by this function, small perturbation function f, and you study the stability. This is a different, interesting direction. This is something else that we're interested in here. Okay, so this is the theorem stated in I tried to do it in as much of a general way as possible without ugly details. So what does it say? It says that if you have the integrable problem and the non-integrable problem, where the data are in some suitable function space that I'm not going to specify now, and assuming that the solutions exist over some maximal time of existence given by this, if in addition you assume that the data, the size of the data is of order epsilon, where epsilon is a number between 0 and 1, not necessarily small, but less than 1. But the difference of the data in this same space is of order epsilon to the third, then you can prove that at least for some non-zero time between 0 and t max, okay, maybe t max, but at least non-zero, positive time, the solution, the difference of solutions remains of the same order with a different constant perhaps. So this is the result, not in a very precise way, but I think it's the best way to present the essence of it. Okay. Okay, so I have 5 minutes. Yes.
Okay.
Or
How many? I thought you had a longer talk.
do I? Oh, I thought you weren't joking.
No.
I'll take it.
It's okay, I'm the chair. No.
Okay, I'll take an hour. Okay. Okay, so I appreciate it. So for the let me tell you, let me focus on 2 different scenarios here, because this kind of analysis can also happen for zero boundary conditions. I know I've been talking about non-zero boundary conditions. What about zero boundary conditions? This is interesting, or I should say it's a simpler case, because in this case, the problem is globally well posed, even in the non-integrable case. So for any nonlinearity bigger than or equal to 1, the problem is globally well posed in H1, the Sobolev space H1. So you have data in L2, and then the derivative is also in L2. That's all we're saying. If P is greater or equal to 2, you need to assume small data. But this is a well-known result from a while ago. So in that case, your maximal time of existence is as much as you like. And so here's how a more precise version of the theorem looks like. If you assume this condition I showed you earlier, now at the level of what space? L2 for the difference of the initial data. Of course, you can make them the same, by the way. This is a more general version. And individually in H1 that have norms of order epsilon, then the solution in L2 of the L2 norm of the difference of solutions is also of order epsilon, like the difference of the initial data. And you can measure things in L2, or if you add stronger assumptions on the difference of the initial data, you can measure them in other spaces. H1, for example, that involves measures other things as well, like gradient. So qualitatively it gives you more information. And also point-wise estimate of infinity. So this is the theorem in the case of zero conditions. Why is it interesting? Because it tells you that, for example, if you have the same initial data, which you can always assume for the two equations, at least for small size, relatively small size solutions of the integrable model, you can expect that these solutions persist in the non-integrable setting at least for some time. This is evident by this inequality which you can obtain through the analysis that tells you that the difference U minus capital U in this space H1 satisfies this bound. So if you think about t here, the time being, let's say, of order 1 over epsilon squared, then this bound becomes of order epsilon, which is still pretty small. So that's how it. So let me show you some numerical simulations to digest this better. For example, if you take the bright solid for both the integrable and non-integrable models with these parameters, it's not visible here, but this implies that the epsilon that we have been assuming in our theorem is 0.2. 0.2, okay. So then you go like 1 over 0.2 square, which is about, how much is that, 25 or something. And you expect that at least for this range of times, you're going to have some proximity according to the theorem. And you can see that in different norms, L infinity norm, the L2 norm, and the H1 norm. This is for the power nonlinearity with of order 7, I believe. And this is the Zakharov one, which does actually much better, as we already knew from the work with Gino, Stefano, and Sita. And you can do other things. You can do collisions of solitons. Okay, so you have this is the fast bright soliton collision here, where you see that the integrability persists in the non-integrable case. You have the almost elastic interaction here, and also in this is the power, and this is the Zakharov case, which is beautiful. You also have bad scenarios. Here is one where you have slow bright solitons interacting, and you see that integrability is lost. You have energy trapping here. This is definitely not consistent with the cubic case. These things are a bit better here, but still it's not as good. Okay. And I have maybe 2 minutes to conclude. Should I start late? I don't know. A couple of minutes just to finish with the non-zero boundary condition. So back to the beginning, in a sense. So U here is assumed to behave like this. So this is motivated from the previous analysis in some phase times zeta of x, where zeta of x is a function that goes to some values that are equal to Q0, some constant at infinity, and has some other properties. This is pretty standard in the analysis of this kind of problems. This is Zipf space x1, where zeta is bounded and zeta prime is equal to 2. It doesn't matter, not that important. So what do you do in that case? In that case, the analysis that we did for the zero boundary conditions doesn't apply right away because you don't have the zero boundary conditions. So you make a transformations. You remove the phase as we did before, and then you also remove the background, and you get this modified system of Schrödinger equations for which you have zero conditions of infinity, and so you can do some analysis using Fourier transform. Then I'm going to spare you the details and just make some comments. What's the difficulty here? First of all, we don't have global well positives. that's still open. Even local existence is kind of semi-open. There's some work by Munoz that settled some cases, but not everything. So that's another component that needs to be done here. But anyway, you can still look at the difference of the modified problem solutions, which amounts to this difference for the original problems. That's interesting because we have these rotations that are apparently do appear in other places. From the comment you can announce both. You also have to prove at least local existence, which you need to say something. And here are some pictures to conclude. So as predicted by the theory, and these are simulations. This is the integrable model. This is non-integrable power model. This is saturable model. You see again the same pattern emerging as corroborated by or predicted by the theory. The norms here in the case of power and saturable in various spaces. And one last picture just to show you that not everything is great. Okay, this is for time between 0 and 10. If you take longer times, things are not as pretty. This is the integrable model. The saturable model is pretty close. The power model departs from integrability here. There's definitely disagreements. So I guess the bottom line is that proximity persists for some time, not forever. Thank you so much. And here are a couple of events upcoming at the University of Kansas. If you're interested, let me know, and I'd be happy to have you in Lawrence next year.
Okay, maybe there's time for a question for Dionyssis.
You probably mentioned it, missed it. How does your estimate depend on the choice of the function and for the non-linearity?
So let's see. I'm going to show you. Yeah, it does depend, and I should have said this. So, for example, in this case, with the local existence, we only work with we only do it for either power or saturable, not the general model. For example, it depends. Let's see. Yeah, so these are the parameters that the constants depend on, and this parameter C here, you see this sorry, K is the one that is the assumption of the nonlinearity. So I guess there's constants accumulating through the estimation that will show up for sure.
I had a question or two about the rate of Jones.
Okay.
So I was wondering, is it an order one perturbation of the field, or is it a smaller perturbation?
It's a leading order contribution to the asymptotics. Is it what we are asking? Yes, it's leading order.
Then would be interesting to compute sort of the speed of the wave and see if it satisfies some version of a kinetic wave.
So we have a formula for the speed, so that's how we identify it. We have a
come from some level set of the G function.
yes, exactly. It's exactly you know how it looks. Yeah, so we have an equation.
But then it's a separate matter that satisfies the equation for the velocity.
Right.
As if it were the solid.
And we haven't done this one. That's
All right, well, let's thank Dionyssis again.